In programming, data types are fundamental concepts that define the kind of data a variable can hold. They are crucial because they determine the operations that can be performed on the data and how the data is stored in memory. Most programming languages use 5 main data types: integers, floating point numbers, characters, strings, and booleans. Understanding these data types and their applications is essential for writing efficient and error-free code. Integers represent whole numbers, both positive and negative, without fractional or decimal components. They are used in situations where precise counting or discrete values are needed, such as counting items, storing ages, or tracking scores in a game. Depending on the language and the size of the integer, it can occupy varying amounts of memory, typically expressed in bits. Floating point numbers, in contrast, represent real numbers and can include decimals and fractions. They are used for measurements, calculations involving precision, or any scenario requiring continuous rather than discrete values, such as scientific computations, currency calculations, or temperature readings. However, it is important to note that floating point numbers can introduce rounding errors due to the way they are stored in binary format, so they must be used carefully when precision is critical. Characters and strings deal with textual data. A character is a single symbol, such as a letter, digit, or punctuation mark, and is often enclosed in single quotes. Strings, on the other hand, are sequences of characters and are usually enclosed in double quotes. Strings are used to represent words, sentences, or any text-based data, making them essential in applications involving user interaction, document processing, or web development. Booleans are the simplest data type, representing logical values of true or false. They are used in conditional statements, decision-making processes, and situations where binary choices are required, such as whether a user is logged in or a condition is met. In programming, it is possible to change data from one type to another through a process known as typecasting or type conversion. This can be done explicitly by the programmer or implicitly by the programming language. Explicit typecasting involves using specific functions or syntax to convert one type to another, such as converting an integer to a string for concatenation or a string to a float for mathematical operations. Implicit type conversion, also called type coercion, occurs automatically when the language determines that a conversion is necessary, such as treating an integer as a float in mixed arithmetic. For example, in the expression 5 plus 2.5, many programming languages will implicitly convert the integer 5 to a float to ensure consistent handling of the operation. Using the correct data type for each variable is vital for efficient and accurate programming. Choosing an inappropriate data type can lead to errors, inefficient memory usage, or unexpected behavior. For example, using an integer to store a temperature reading might suffice in some cases, but if precision is required, a floating point number is more appropriate. Similarly, storing a Boolean value in a string variable might work initially, but could complicate later operations, such as logical comparisons or evaluations. Additionally, selecting the wrong data type can lead to wasted memory. Using a large integer type, such as a 64-bit integer, to store small numbers like 1 or 2 consumes unnecessary resources, particularly in applications where memory is constrained. In summary, understanding data types is a cornerstone of programming. The 5 main data types, integers, floating point numbers, characters, strings, and booleans, each serve specific purposes and are suited to different kinds of operations. The ability to convert between data types enhances the flexibility of programming, allowing developers to adapt to varying requirements. Selecting the appropriate data type for each variable ensures that programs run efficiently, perform as expected, and use system resources effectively. This understanding enables programmers to write robust and optimized code, laying a solid foundation for more complex programming concepts and applications.